Thank you for downloading the Start the Week podcast from BBC Radio 4. For more information, go to bbc.co.uk/Radio 4. Hello. After the merry and justified hullabaloo over BBC Sports Personality of the Year, there's an interesting response in today's Times newspaper. Why don't we focus just as much on our intellectual world beaters, particularly in science, asks its columnist Matthew Syed. Youngsters are inspired to take up sport, he points out, but scientific progress provides benefits which cascade through society, reducing suffering and raising living standards. Well, on cue, today we're looking at the realities of a year in British science with Professor Sanjeev Gupta, who's part of the team studying the surface of Mars, with Ewan Birney, part of the ENCODE project working on human DNA, Helen Bynum, author of a new study of tuberculosis, a disease that's coming back to bite us, and Peter Wothers, the Cambridge chemist and self-described modern alchemist, who is giving this year's Royal Institution Christmas lectures. Welcome to you all. It's interesting, even as I'm describing you, you're all working in teams. One of the points that was being made by Sebastian Coe after the Olympics is that sport is all about teamwork, and that is something where science is just the same. Peter?
Absolutely. I mean, all research groups now, you can't do what people did sort of 200 years ago, where one person could be making major discoveries. I mean, nowadays the research groups are carried out with sort of 50 people in them or whatever, and there's often collaboration between different groups as well, and they're absolutely enormous. But this is throughout all branches of science, really.
You all have your tribes in which you're embedded.
Yes, so in the ENCODE project, I was just one author of 442, in fact. But as well as the kind of project level, there's really a field, there's a whole group of scientists, sometimes working in quite small teams, but collectively representing a big movement in the field to try and sort out an area. So you have differences of very big teams that work together to do science, and smaller groups as well, all together trying to understand something.
I talked about British science, Sanjeev, but in fact you're part of a rather small number of British scientists working, in this case, in a mainly American team on the Mars project.
That's right. This is an American project, a NASA project, but actually most of my career I spent working in very small teams with myself or a couple of students, so this is quite unusual for me now to move into something that involves 200 or 300 people.
Oh, based in Pasadena?
All based in Pasadena, or all around the world, actually, and we do most of our work remotely by telephone.
Helen Bynum, in your book Spitting Blood on the History of Tuberculosis, you describe lots of different groups and teams of people trying to crack tuberculosis through the years. But today, when we have these new resistant strains of tuberculosis, we'll talk more about it later on, again, that's going to depend upon teams of people.
Absolutely, and people from different ways of looking at the same problem coming together, so not just people in the laboratory, but also people who actually work in the field as clinicians and healthcare workers. Those are also going to be part of what will be the modern team to try and deal with tuberculosis.
So, sort of fewer people standing on the front of the stage taking all the glory for themselves, except for the fact that Peter Wothers, that's exactly what you're going to be doing at the Royal Institution Christmas lectures. Long established, goes all the way back to Faraday and stuff, doesn't it?
That's right, yeah. Yes. So, I mean, it's fantastic to be bringing some chemistry back to the Royal Institution, I think.
Well, I'm interested in the title that you've chosen, because I suppose one of the things for the non-scientifically educated, and that includes kids, but many adults, of course, there's this sense that modern science is impenetrably difficult. And you've chosen an almost homely word, alchemy, which makes one think of kind of Tolkien and hobbits and funny hats and so on, to describe yourself. Why modern alchemy?
Well, I think in a way that all chemists are modern alchemists. I mean, the alchemists are trying to sort of change one thing to another, but that's exactly what modern chemists are doing. But we just know a little bit more about what's possible and what's not possible now. So we know some of the rules, I think, that define what we can do.
Yes. So before we come on to the lectures, what is your particular area yourself? What do you spend your day and day
Well, now in the
doing.
university, I'm dedicated to teaching in the chemistry department, which is rather nice, which I think is incredibly important, and getting across the ideas of science, particularly chemistry, to a wider audience, to the public and so on.
And how much is that still kind of bangs and smells and experiments?
Well, I think this is one of the exciting things about chemistry, that it is, you can have some spectacular demonstrations, and there will certainly be some very spectacular demonstrations in the Christmas lectures coming up. So there's some things that haven't been done before, which is, for me, very exciting to see. Some good flashes, good bangs, yes. A few smells as well.
Yeah. But of course, the intention is to intrigue and lure people into the world of science a little, so that they explore it more. But there's no getting away from the fact that for all of you, this is hard work. I mean, there's a lot of learning and tough study, not least with the periodic table that you have to do before you're off first base.
Well, it's trying to show how it all does make some sense, because I think a lot of people say, I hated chemistry at school. I get this so often when you say, when people ask me, what do? I say, I'm a chemist. And they say, I hated chemistry at school. But I think it's because they don't quite see how it all fits together. And this is one of the things we're trying to get across, exactly what the elements are and how we encounter them in our lives and so on. And also some of the sort of more, newer applications that we're finding for them.
And given what's going on, for instance, in physics these days, does it still make sense to divide all scientists or all science teaching into chemists, physicists and biologists?
Well, certainly at the research end, I mean, all of the sciences absolutely blur into one. I mean, there are seamless boundaries between everyone, and I think everyone sitting around this table would agree with that. But there are subtle differences between each of the sciences. I think chemistry is all about how things are reacting together. It's that interaction. And that's slightly different from the perspective of a physicist, but nonetheless, I mean, a good scientist has to make sure he has an understanding of all of these different areas. And as I say, in the physics labs, we will find chemists, biologists, and so on, and similarly in chemistry.
I'm interested in this. I mean, do chemists have a particular way of looking at things? Is there a chemist's mind which is different from a physicist's mind or a biologist's mind? I'd be interested in all of your responses to that.
I'd say definitely, yes. I mean,
and so what is it? What is a chemist's mind?
For me, I mean, it's about how these atoms are interacting with each other, and when different atoms come together and so on. And it's that it's the interaction for us that's the important thing. Why one element is so different from another, and how when it's bound into a compound or a molecule, how that affects the behaviours of that molecule. So that's the chemist's perspective.
That's you and Bernie?
I really appreciate that. I now know quite a few chemists. And of course, as a biologist, I was trained as a biologist and a geneticist. We are chemical machines that work. I mean, we are all here, and we are the product of physics and chemistry. And then, amazingly, we get to speak on Radio 4.
And we're electrical machines too, as listeners to this programme will remember. Yeah.
Yes, indeed. And but the chemists, knowing the chemists in my field, they end up just being entranced by how is it that this very small set of atoms does this one particular thing and not this other thing. Whereas I'm often much more interested in how is it that this sort of amazing program that starts with one cell ends up with an organism like ourselves. It is, though, the two things, like Peter says, have to be related. I have to know enough chemistry to at least fake it at the right time. And there are some chemists who have to know enough biology, vice versa.
Sanjeev, as a rocks man?
Well, for us, actually, our experiments have already happened, and they often happened millions and billions of years ago. So our task as geologists, kind of like detectives, we want to try and reconstruct those experiments from the bit parts, basically. So you've got parts of experiments that happened, and we try and reconstruct the processes and what actually happened. So the history is important for us.
So you're a forensic chemist coming along at the scene of the crime.
That's right, forensic chemists and physicists, actually. So we're trying to understand that physical and chemical evolution of the Earth and other planets. And we use all the clues that we have before us.
Helen, do you think there are different mindsets that you can trace when you're looking at something like the history of a disease? Different people coming at it from...
Yes, you can. And I think the other thing that's important historically is the idea that life is somehow something different to physics and chemistry. And I think that is one of probably the great things that we've learned over the period of that we've been doing science is that we're the same. And I love the fact that Peter's doing the four original Greek elements, because the Greeks had the idea that everything was made up of these same four: earth, air, water and fire. And that was the same. Everything under the level of the moon, under the heavens were different, but under the level of the moon, everything was the same. And I think, in a way, we've come back to thinking about that because we now understand that
at fundamental levels,
at the elemental level, the things that make us up, we are all the same.
That's very interesting. You have mentioned experiments, Peter, and you are sitting there with a very large red shiny balloon on the table with XE written on it. You must explain that.
Well, but as you say, it is sitting on the table. I just thought it's quite remarkable. So this is an element. It's quite a rare element. I shall pass it over to you. It's perfectly safe, don't worry. But
it's heavy.
It is, isn't it?
It's
it really
heavy.
It's quite surprising.
It's a balloon which goes down, not up.
And it swings like a pendulum, actually. Look at that. I mean, it's not much fun at a party, I don't think.
No.
But
well, we're not going to pop it because we'll...
No, you can't. That's over £100 worth of xenon in that balloon.
Right, OK. Well, we definitely won't pop it. very, very interesting.
But, I mean, so these are actually single atoms. And this is the interesting thing about this is a family, a group of elements called the noble gases. Helium is one of them at the top, which is, of course, the lightest. And this is the heaviest stable element, xenon. But, I mean, this has...
Where is it found?
It's extracted from the air. Xenon is, but it's only present in tiny, tiny quantities. But the remarkable thing is that, I mean, this is now finding uses in medicine. So I went up to Sheffield University with Jim Wild's group, where I've had my lungs imaged using atoms of xenon, which is incredible. So it's pretty inert, like helium is, but and you can also do a similar experiment with helium, a type of helium, a very, very rare type of helium. But I say it's quite remarkable just detecting these individual atoms in your lungs, and you can tell if somebody's a smoker or if they've got asthma. He knew that I had a cough just from imaging these.
Or indeed, whether they've got tuberculosis, which
yes.
takes us to Helen Bynum's History of Tuberculosis, Spitting Blood. One of the things I hadn't realised before I read your book, Helen, was that TB has been part of the human experience as early as we can know.
It seems to have been that way, yes. I mean, it used to be thought that it was that it had been there as long as we had been sort of come out of the Stone Age and lived in settled communities. But it now looks, from sequencing of the DNA of the organisms and from a particular fossil find in Turkey from about 500,000 years ago, that in fact we may have been carrying precursors of our modern TB germ around with us for a very, very long time. And in fact, I think I think you might expect that, actually, because TB is a very chronic disease in most cases, and therefore there's a sort of degree of accommodation between parasite and host, which tends to be the case in long-standing, long-evolved parasitic cases.
And in culture, TB has always loomed large. Violetta from the opera, of course, right at the end, Spitting Blood. You called your book Spitting Blood, and people think of Keats, and you've got some very interesting passages about Keats dying in Rome of tuberculosis. But you start the book with George Orwell, which is interesting because lots of people know, I suppose, that he died of TB. But the awful nature of that struggle at the end of his life is something certainly I hadn't appreciated.
Well, I had a lot of fun deciding who was going to be my sort of opening case history, so I got to read lots and lots of biographies that have been on the shelf for a long time. I've always admired George Orwell's writing, but the thing about George for me was that he was such a wonderful combination of somebody from a better sort of middle class social position. But he spent a lot of time when he was doing research for his sort of left wing political writings, slumming it, living rough, not eating very well, certainly not sleeping in very good circumstances. So he experienced both sides of life, if you like. And also towards the end of his life, when there are the wonder drugs have come in, streptomycin and then PAS, they don't work for George. And so, although he's on the cusp of the great new modern era of antibiotic medicine, it doesn't work for him, and that was very poignant because he represented lots of other people's cases as well. And I think because he had the disease for a long period of time, and tried lots of the standard cures that were available before the antibiotics. Again, it was a wonderful way to explore what the disease had meant over quite a long period of time in the 20th century.
It is a deeply unromantic disease once you start to read exactly what it does to the lungs and other parts of the body.
Absolutely,
of course,
it's a ghastly disease. Actually, it really is.
And it's always been a disease of poverty, or certainly crowding, spread in the air, and moisture and particles.
That's right. I mean, it's if somebody has pulmonary tuberculosis, if it's in their lungs, every time we speak or sneeze or just talk to each other, cough or sneeze, talk to each other. We exude these little aerosols, and they have the bacteria on them. And then if somebody else breathes them in, they go down into the little air sacs right at the end of the lungs, and that's where they sort of lodge. And then they can, they elicit an immune response, which means that a certain kind of cell, a macrophage cell, will try and engulf them. And they do that successfully, but they don't kill the bacteria. And so over a period of weeks, that process will go on, and you might be sick, you might have a bit of a cold, a bit of a fever, but you probably wouldn't know that you're necessarily going to become seriously ill and ultimately die of the disease. Because
it basically eats out the lungs, doesn't it?
Does.
So there's very little of the lung left.
That's the secondary sort of immune response as well.
So before we get to the great modern breakthroughs in tuberculosis, we were hearing about alchemy, and you talk quite a lot in the book about the four humours of traditional Roman and Greek medicine. But actually, it's not entirely hopeless. There are ways of treating or dealing with people with tuberculosis which at least extend life. There's a lot of travelling. There's a lot about getting to the sea journeys and getting to the right climate and so on, which does seem to help people for a bit if they can afford it.
If they can, most people who are unfortunate enough to breathe in the bacteria, in about 90% of people, it will become locked in a tubercle. Hence that's where we get the name from, and that will be the end of their disease. For the unlucky 5 to 10% where it goes on to produce a primary infection, how far that goes and how bad it becomes does depend on things like your socioeconomic status, and so feeding people up and taking care of them can actually be very important. The idea of
sending them up mountains as well.
Yeah, the idea of travelling for health is I probably would say wasn't a great success, but perhaps it certainly probably made you feel better while you were doing it. The idea was that you would be exposed to a different kind of air, and air was the element in which was most in contact with our bodies. And therefore, the idea was that you could change the circumstances in which somebody was living, and that would make a difference. Now, we might find that rather laughable, but within the system, within the Greek humoral system, it did make sense.
Yes. I mentioned Violetta earlier on, but there's a terrible, wrenching bit in your book when you're talking about Verdi's La Traviata, and she dies, of course, of TB at the end. But the notes she was singing, there's no way that somebody with tuberculosis would have been able to make that sound. Is that right?
Yes. I mean, particularly when it's got into the voice box, when it's destroying the voice box, people often lose...
The high B flat.
Often lose the ability to speak completely. And there's an amazing quote in Franz Kafka's diaries where he describes sitting opposite a friend of his who's got laryngeal tuberculosis, and this guy's voice is cracking up. And Kafka writes about how he's actually sort of spitting out parts of his very body, as it were, into the room in which they're talking. And it would have been the same for the kind of disease that Violetta was supposed to have. But I think we have to give Verdi the artistic licence.
He's an opera composer. Yes. He has to have his high flat at the end. Now, for an awful lot of people, the notion that tuberculosis is coming back, I'm afraid, is news. I mean, it's clearly spreading again fast, partly thanks to resistant strains.
Yes, that's right.
Just because there was a period where it looked like it might become one of those diseases that was going to be almost eradicated, at least in the West.
That's right. Well, and I think people were talking reasonably sensibly about control. And control meant not necessarily that there would never be another case, which is eradication, but that you would be able to detect and treat those people within a normal healthcare situation. So if somebody was coughing for a long period of time, perhaps they were a bit febrile, you would be able to make sure that they had a good diagnosis, and then you would be able to treat them. That was what changed when we discovered antibiotics against tuberculosis. Something that had previously been incurable became curable, and that was a very dramatic moment in a sense. I mean, it wasn't just one moment. It was discovery is never just one moment, but there was a certain period when things changed.
So why is it coming back?
It's coming back because it never went away in most of the world.
And it's a disease of poverty.
And it's a disease of poverty, it's a disease of malnutrition, it's a disease of poor circumstances. It's also a disease with comorbidities. So anywhere where you have people with other infections, like HIV, AIDS, that's the other reason that it's come back, is because the body is compromised. It's much less able to fight off infection by itself. The other thing is that we made drug-resistant strains of tuberculosis because people didn't, for various reasons, continue and have the full course of drugs that they should have done.
Sanjeev.
So with the rise of these global megacities, this is a serious problem now to consider?
A very serious problem to consider, yes. And I mean, we're lucky in the West because we can always mop up the cases. So far, we've always been able to do that. But with the rise of these extremely drug-resistant cases that have turned it back into an incurable disease again, if those organisms start to spread in the community as they are spreading, then we will not be able to deal with them.
You and Bernie?
And I think it's also true that the antibiotics treatment, as well as people not completing their treatments, there's our use of antibiotics in intensive farming. And I know that there's quite a lot of evidence that the difference in our natural microbiota in the guts are different country by country because of the way that we're using antibiotics in farming. And I think there's quite a lot to learn and discover about how both our kind of healthy microbiota and these unhealthy things, and then they trade resistance genes between them. So I'm sure
classic case of working across disciplines, actually.
Yes, absolutely, between these different areas as well, for sure.
And recognising that antibiotics, I mean, I don't want to sound pejorative. I don't want to sound like I'm condemning people. People don't necessarily willfully not complete their course of drugs. And we're talking about 18 months or longer. I mean, this is a long time to be popping large pills with unpleasant side effects. So, I mean, let's not be judgmental about this. And you have to be in a situation in your life where that really is terribly important to you. And if you're struggling to get enough to eat or find a job, maybe missing 2 or 3 days of your pills isn't that big on your agenda, particularly when you've started to feel well again, which of course we all know when we get a week's course of antibiotics. After 5 days we feel great, but you must do the extra 2 to get it up to 7.
Well, let's move on then to an area where certainly the headline writers are constantly demanding breakthroughs, health breakthroughs and instant magic treatments, which is DNA mapping and sequencing. You and Bernie, as I said, you're part of a large team, a very large team. Just try to explain to us lesser mortals exactly what you do and even what you call it.
Yes, so I'm from the European Bioinformatics Institute, and bioinformatics is a clumsy word for trying to understand biology using computers. So we mainly do it in computers rather than with wet experiments. And recently, what really the whole field in this area has over the last 4 or 5 years has developed new ways of looking at how DNA works in our cells. So just to remind you, each one of our cells, we have about 1 trillion cells in our body, and each one of them has the same genome, the very first genome that was at the zygote when sperm met egg, all the way back there. And that's a 3 billion letter book. So every one of our cells has this 3 billion letter book. And rather remarkably, our neurons use that book in a different way from our liver cells, and they use the book in a different way from our hair cells. And so what we were studying was how is it that a brain cell knows that it's a brain cell and knows to read these different places in this book to do brainy things.
It's really a question of switching on which bits when and so on.
Absolutely.
And this is when the phrase, I think you're slightly queasy about, junk DNA started to be used.
Yes. So unfortunately, we for a variety of reasons, we've chosen a phrase in the lead up to this, or at least for the public understanding, junk DNA, which is a bit of a dog whistle, I think, to headline writers.
It's nice and short.
It's nice and short. And there's two problems about it. So one is that there's a sort of scientific debate about precisely what it means, and in fact those are two very small words, and so you can get lost in that debate. And the second thing is that it can be slightly misleading because people overinterpret what the word junk means. And so really stepping back from all of that, what we're discovering is how a lot of the different parts of this book work, and how they work actually biochemically. And just to make life a little bit more confusing, if it wasn't already enough, we can see these places that do a lot of interesting things biochemically, but might actually not be that important for us, for our organism. So they do something that looks interesting to the scientist, and yet if they didn't,
the general reader would be boring pages.
Boring pages, and indeed. So if it's not junk DNA, what would you prefer to call it? Enigmatic DNA or something? Enigmatic DNA. You heard it here first. That's very good. And in terms of the importance of enigmatic DNA and how much, just tell us a little bit about that. So 10 years ago, when the human genome was sequenced, we knew about protein coding genes, and these are the things that make proteins, keratin in our hair, the proteins of our retina, everything that you see in us. The starter motors, as it were, for the kind of the final molecular machines. But those only were about 1.5% of the DNA encoded those protein coding genes, and so we had a big set of enigmatic DNA. What was the rest of it for? Well, and maybe it wasn't for anything at all. One shouldn't walk in here thinking that everything was important. What we did know, though, was that these different little machines were being switched on and off in very specific cells. So your hair cell makes keratin, your liver cell makes all the enzymes that digest, help process metabolites and things like that. So we knew there must be switches, they must be somewhere, but we didn't really have a big catalogue of switches. And so the big thing that we did, and just to say we're part of this bigger movement in this area of science with many, many different groups doing this, is really have effective experiments to catalogue where these switches could be. And there are more switches than we ever expected, certainly than ever I expected. And then rather beautifully, these switches also line up with another line of investigation where people have been looking at diseases like heart disease, schizophrenia, and all these other diseases. And very often the places that change your risk for these diseases have been out in this enigmatic DNA, far away from genes. When we look at these switches, those switches very often line right on top of these places that are changing your risk for a particular disease. This could be very important, but you live in an area of science where not the media simply, but public expectation is constantly pressing forward for when are you going to solve this disease problem? When are you going to resolve that? If we can read the whole of the genome, surely you can answer this or that. Now, we've talked about TB being a disease of poverty, but presumably a lot of what you now have to do is just simply manage expectations. And we're working our way through the book. Just be patient. There's that, and also we're in a situation where we have to, talking about multidisciplines, we have to bring in our clinical colleagues, and there are very different cultures from research science to clinical work, and so I've got to know a lot more doctors. I've discovered quite firmly that I'm not a clinical doctor. It's an obvious statement, but one needs to go through that experience. And so, indeed, there's a kind of management of expectations, and actually in both directions, that it's neither hopeless, but nor will it happen tomorrow. So we are more Mo Farah than Usain Bolt. It's a long marathon-style process over the next decade, I think, for us to discover how best to use this information. the us there is not just scientists. In fact, it's mainly doctors, to be honest, for doctors to discover how best to use this information.
Peter Wothers.
So you say you're working your way through the book, but isn't the case that you need a lot of books to try and work your way through in order to understand what's going on here? I mean, isn't it by making comparisons between lots of different DNA? And is this a problem trying to get lots of different DNA to actually sort of make these comparisons?
So one of the really powerful things that have come over this decade is that our ability to read the book has got cheaper and cheaper. So now, 10 years ago, we effectively read one person's genome. These days, we routinely think about 1,000 or 500 people. And coming up in the future, it's going to be more like 100,000 genomes to be sequenced. There's another particular disease where this looks really effective, and that's really a class of diseases being cancer. So cancer is when a cell goes out of control, and very often, nearly all the time, there is a DNA change to that cell. So a very powerful technique is when somebody has a cancer, you sequence the DNA of the cancer, and you have to sequence the healthy DNA of the person as well to know where the differences lie. And now you have a new way of classifying cancers. So you can classify them where they came from. You can classify them how they look down the microscope. Now you have a third way, which won't actually replace those other two, but will add a lot more information about how molecularly the cancer looks like.
And people are starting to have their own DNA read commercially now, aren't there? There's a thing called 23andMe, I think.
That's right. That's kind of at the moment that's slightly doing it on the cheap, which is not a dreadful thing at all. That's the way it's been done. So that's called genotyping. In fact, I've been 23andMe'd myself. But really, the future is going to be more about the full-blown genome sequencing and doing it in the context of proper healthcare. So 23andMe is interesting, it's fun, but
it's a sort of commercial thing, I should explain, yes. Sorry, Helen, you wanted to come in there?
Well, I just like to... I mean, there's always this sort of spectre in the background that this is the new eugenics. I mean, how do you feel about that? I
think that's both overplayed and also something that we've had to deal with in society before we had DNA. So inequalities and, for example, abortions on the basis of sex in China and India have been going on long before one was able to map this DNA. So I think the mistake is to think that DNA is somehow special and changes things and gives us new challenges that we haven't faced beforehand. Very often the ethical challenges that we're faced with DNA are very analogous or sometimes identical to current ethical challenges we have in medical practice.
Yeah, you can't just simply use the science to replace the ethics. So they always go side by side. Well, we've been talking about something that is extremely popular in the media imagination and very expensive. And we're going to carry on with something which excites headline writers and is very expensive. Because Sanjeev Gupta, you are part of the rover mission on Mars. It's called Curiosity, which is a very, very good word for that. And you have this kind of great big mechanical bug about the size of a car, family car.
It's about the size of a Mini Cooper, actually.
About the size of a Mini Cooper, very, very slowly inching its way across the surface of the red planet. But what you are doing as a geologist is not so different from what a geologist would have been doing 150 years ago.
Yeah, taking that book analogy further, in the last 200-300 years, geologists have been reading the record of Earth's history by looking at the sedimentary layers, the rock layers that we see exposed, for example, along the Dorset coast or in the Grand Canyon. And our next step is really to be able to do this for other planets. And this is really the task of this rover. One of the first tasks is really to try and reconstruct how the surface of Mars has changed by looking at individual rock layers, and as the rover slowly trundles along looking at different rock layers, try to work out what those rock layers are.
And it's able to sort of literally to suck up quantities of rock and analyse it.
Yeah, it's an amazing laboratory here. So actually we can do experiments on that laboratory, in this laboratory. So the first thing we do is really we first take pictures. That's where I come in. I'm a geologist. I look at those pictures. I interpret those. I try to reconstruct what those mean. I try and work out what those rock types are. Some of our most basic arguments are, what is that rock type? We don't know. And then the next task is, we can't actually examine every single rock with our chemistry instruments. It would take too long. So we have to pick. So it's kind of an economic decision we have to make. So we have to find the best rock we can. And we haven't started that process yet, but we have ingested sand. So we've taken sand, sieved it, shaken it in a cup, which is amazing, tens of millions of miles away, and actually ingested it into the rover.
And this is all being done by programming and then passing the messages by satellite?
That's right. So basically what happens is that we'll arrive at a site, we work out our location, we'll think about what we want to do, and the scientists, who are usually not allowed anywhere near the rover or the coding, come up with some general plans of what they would like to do. And this is quite it happens on a very short time scale, so we might have an hour or so to work this out.
Decide whether to go left or right.
Absolutely,
or
where to take a photograph or what to do. And then what happens then is that we give our general instructions, and then the engineers who really make this happen, the engineers are extraordinary, they will turn this into computer code and a series of commands that are then uplink, that are sent to the rover at the end of an Earth day and at the beginning of a Mars day, so that when the rover wakes up and we play it music to wake it up,
yes.
It can receive those commands and carry out the instructions that we've sent it.
And this is all taking place on a landscape which is, of course, unfamiliar, but is in some ways curiously romantic sounding. It's this enormous crater that you're working your way with, Mount Sharp, I think, in the middle of it, pointing up this little mountain.
Yes, so we've got this crater that's about 150 kilometres wide, but the key thing about it is it's got this mountain, Mount Sharp, as you said, which is about 5 kilometres high, and this is made up of layered rocks. So we believe that these are layered sedimentary rocks. So they're like the pages in a book that I was talking about. So the overall plan is, over the next few years, and this rover is actually powered by a nuclear reactor, so it's going to go on for some time if we don't break some of the instrumentation earlier, but we can basically climb up this mountain, progressively reading these rock layers. As you climb up, you go from the oldest layers at the bottom, which we think were perhaps 3.7 billion years old, something like that. That's sort of when life kind of started on Earth, and basically go up through younger layers. So we're actually reading that environmental history, the ancient environmental history of Mars.
And all the headlines, of course, are about will any evidence of life be found, by which we're probably talking about tiny biological forms deep underneath the crust.
That's right, and I think obviously that's the excitement, but I think we have to step back. Science is a slow process. So really this mission isn't about life discovery. It doesn't have the capability of life discovery. And what we want to do is really to find the environments that were habitable for life. So it's a step, basically. I mean, if you imagine that you're landing a rover, imagine you're landing for the first time on Earth. Where do you start? Of course, life is everywhere on Earth, but imagine you're going to a new place. You don't know where to begin. So you have it's worse than a needle in a haystack, really.
Peter Wothers.
I have a chemistry question for you, actually, relating to this. So, I mean, everyone's always focused on water on Mars and whether there was any, is any, or where it is, and so on. But so here on Earth, I mean, one of the lectures that we're looking at in the Royal Institution Christmas lectures are the salts that you find in the water. So, if there's no water on the surface, does this mean you have a lot of sort of water-soluble salts in the rock? I mean, does this lead to completely different sort of geology on the surface then, of things that you wouldn't normally just sort of find lying around on Earth?
So what we're looking for is the ancient movement of water and the ancient reactions of water. And so one of the things we know about, and the reason this site was chosen, is that from orbit, from the satellites that go around, the spectrometers could pick out traces of clay minerals and sulfate minerals, and these are minerals that are formed through interaction of rocks, maybe basalts or whatever, with water. And so we need to ground truth that. And the key is that precipitation.
So you need to ground truth that.
Oh, so actually see it on the surface.
Right,
this has been done from satellite, and we want to actually be able to look at this and work out those minerals. And the key thing is that this rover actually has an instrument, an X-ray diffraction, that can actually precisely work out the mineralogy. And the beauty of some of these minerals, like evaporites or sulfates and clay minerals, is that when they precipitate, when they solidify, they can actually entomb organic material. And that's the key.
Right, so that's it's what's hidden inside them.
It's what's hidden inside. And so we want to first find out whether these minerals exist.
Helen.
I was just. I hope it goes on forever, and that the nuclear reactor doesn't, run out of fuel.
Plutonium battery.
That's right. Sounds lovely,
really
doesn't
cool,
it?
Yeah.
But I wondered whether, on the basis of this, I assume that putting something into orbit around Mars is cheaper than than landing. Whether what you're going to do will inform those, perhaps, how will it relate to missions in the future? I know it's a bit cruel since you're so deeply embedded in the one you're on, but I was just thinking beyond that.
Well, we already have several missions coming up. So Europe is going to send both an orbiter in 2016 and a lander. So it's going to be the first European rover in 2018. And the Americans have already suggested another. So it's step by step. So we're working out the geology of this area and what the rock types are, etc., reconstructing that history. And future missions may go to other places because obviously the geology and the environmental conditions are different. So what we try and work out is what's the best place, where are the best rocks that might have been habitable for life.
But does that not depend on Russian help as well, that landing? And they haven't had a great record of landing on Mars, the Russians, have they?
I think they're going to work very, very closely with ESA, the European Space Agency, in designing a landing system. And so the 2016 orbiter has also got a test landing. So it's going to land and test some of these things. It's always step by step. But I think it's a huge moment for Europe to actually have its own rover.
Ewan?
I find it amazing, though, that this is a science where there are these moments where there's a critical window, and if it goes wrong in that critical window, you don't go back and come back the next day and try the experiment again. Your rover has gone off and in a farball somewhere over Mars. And that must be very scary. I don't know. Were you part of the project when Curiosity landed? Did you kind of cross your fingers? And what did you do?
Well, I was not in the main mission control, but I was in the room where all the scientists were, and there was a lot of tension. I'm not sure we were fully convinced it was going to land. But what was the most interesting thing was that after it landed and the first picture had come down, there were two big screens, one with the press conference and one with the picture, and all the scientists were huddled around the grainy picture trying to work out what was happening. It was almost like the keys had been handed to us.
Yeah. Well, I think I hope we've demonstrated that science is like sport in certain respects. It's teamwork. You've all talked about teamwork. And it takes a very long time. And you don't always get the results you hope. And it's also as exciting as sport. But none of you are going to stand on a podium, I fear, are you? It's never going to be that kind of personality of the year sort of...
But I just think, this is the thing. I get to do what I love doing, which is trying to work out bits of biology. I don't need to... It's just so enjoyable when you're given the opportunity to fool around at this level.
And that's the most important thing, Peter.
But it's interesting. I asked my colleagues the other day if you ask the public, who would they name as a famous scientist? And I think it's really difficult to answer. There are people like Hawking, of course, but everyone knows the sports personalities, the actors, and so on. But the scientists don't really get too much of a look in.
But as long as you're all having fun,
and we are.
Thank you to all my guests. Sanjeev Gupta, we were hearing from just now. Ewan Burney, who's going to be giving a lecture, What Can We Learn from Our Genes, at the Royal Society in London at the end of January. Helen Bynum's whose Spitting Blood, The History of Tuberculosis is out now and a cracking good read. And you can see Peter Wothers blowing things up for this year's Royal Institution's Christmas lectures from Boxing Day on BBC4. Next week, a special programme for Christmas Eve about the power of the human voice with Rolando Villazon, Mark Anthony Turnage, a composer, Mary King and Michael Trimble. But for now, thank you and goodbye.
There are many more Radio 4 arts and discussion programmes to download for free. Find these on the website at bbc.co.uk/Radio4.
Thank you for downloading the Start the Week podcast from BBC Radio 4. For more information, go to bbc.co.uk/Radio 4. Hello, after the merry and justified hullabaloo over BBC Sports Personality of the Year, there's an interesting response in today's Times newspaper. Why don't we focus just as much on our intellectual world beaters, particularly in science, asks its columnist Matthew Syed. Youngsters are inspired to take up sport, he points out, but scientific progress provides benefits which cascade through society, reducing suffering and raising living standards. Well, on cue, today we're looking at the realities of a year in British science with Professor Sanjeev Gupta, who's part of the team studying the surface of Mars, with Ewan Burney, part of the ENCODE project working on human DNA, Helen Bynum, author of, in your book, Spitting Blood on the History of Tuberculosis. You describe lots of different groups and teams of people trying to crack tuberculosis through the years. But today, when we have these new resistant strains of tuberculosis, we'll talk about more about it later on, again, that's going to depend upon teams of people.
Absolutely, and people from different ways of looking at the same problem coming together. So not just people in the laboratory, but also people who actually work in the field as clinicians and healthcare workers. Those are also going to be part of what will be the modern team to try and deal with tuberculosis.
So, sort of fewer people standing on the front of the stage taking all the glory for themselves, except for the fact that Peter Wothers, that's exactly what you're going to be doing at the Royal Institution Christmas lectures. Long established, goes all the way back to Faraday and stuff, doesn't it?
That's right,
yeah.
Yes. So, I mean, it's fantastic to be bringing some chemistry back to the Royal Institution, I think.
Well, I'm interested in the title that you've chosen because I suppose one of the things for the non-scientifically educated, and that includes kids but many adults, of course, there's this sense that modern science is impenetrably difficult. And you've chosen an almost homely word, alchemy, which makes one think of kind of Tolkien and hobbits and funny hats and so on, to describe yourself. Why modern alchemy?
Well, I think in a way that all chemists are modern alchemists. I mean, the alchemists are trying to sort of change one thing to another, but that's exactly what modern chemists are doing. But we just know a little bit more about what's possible and what's not possible now. So we know some of the rules, I think, that define what we can do.
Yes. So before we come on to the lectures, what is your particular area yourself? What do you spend your day and day?
Well, now in the university, I'm dedicated to teaching.
But as well as the kind of project level, there's really a field. There's a whole group of scientists, sometimes working in quite small teams, but collectively representing a big movement in the field to try and sort out an area. So you have differences of very big teams that work together to do science, and smaller groups as well, all together trying to understand something.
I talked about British science, Sanjeev, but in fact you're part of a rather small number of British scientists working, in this case, in a mainly American team on the Mars project.
That's right. This is an American project, a NASA project, but actually most of my career I spent working in very small teams with myself or a couple of students. So this is quite unusual for me now to move into something that involves 200 or 300 people.
Oh, based in Pasadena?
All based in Pasadena, or all around the world, actually. And we do most of our work remotely by telephone.
Helen Bynum, in your new study of tuberculosis, a disease that's coming back to bite us, and Peter Wothers, the Cambridge chemist and self-described modern alchemist, who is giving this year's Royal Institution Christmas lectures. Welcome to you all. It's interesting, even as I'm describing you, you're all working in teams. One of the points that was being made by Sebastian Coe after the Olympics is that sport is all about teamwork, and that is something where science is just the same. Peter?
Absolutely. I mean, all research groups now, you can't do what people did sort of 200 years ago, where one person could be making major discoveries. I mean, nowadays the research groups are carried out with sort of 50 people in them or whatever, and there's often collaboration between different groups as well, and they're absolutely enormous. But this is throughout all branches of science, really.
You all have your tribes in which you're embedded.
Yes. So in the ENCODE project, I was just one author of 442.